All right, let's wait for YouTube to start streaming. The title should be Take Two. Okay, so we're doing Take Two, waiting for YouTube to see that the audio is okay. Good job. All right. So, this is Take Two. So, I'm gonna recap from the last video. Okay, so according to Einstein, so we have a card here with two mirrors and a photon. This is Einstein's thought experiment about a photon clock, a clock, and his explanation for why time must slow down when I'm an inertial observer and I'm observing something moving. When something is moving, its internal clock must slow down. All right, so Einstein said that there is a photon bouncing back and forth. And I don't know if he did it, but everyone uses, when they say photon, they draw like a ball. So photon is like a particle bouncing back and forth. All right, so let's assume that's true and a photon is a tiny particle that bounces back and forth. And then when I start moving, for some reason, that bouncing ball back and forth knows to to do it at an angle. How does it know to do that, right? When I start moving, that bouncing ball should stay bouncing over there, and when the cart moves away, we should lose the photon, according to this thought experiment. So already we're beginning to see that this thought experiment is breaking down. That's the first problem. Okay, so problem one, it doesn't make any sense that the ball should keep bouncing back and forth and then develop this angular bouncing. It's like it's intelligent. It's like it knows we want it to bounce to the opposite mirror as it's moving. So no matter how fast I accelerate, this bouncing photon knows to change the angle. It's like it plays ping pong with me. It's like the video game ping pong. It always knows to hit the ping pong with the paddle. It's like a super genius universe. Anyway, that's right. That doesn't make any sense. How does that work? Okay. Another problem is, why does this ping pong bounce at the speed of light? Why should a particle move at the speed of light? So Einstein says, people say, it's because it's massless, and massless particles move at the speed of light. Okay, so why is that? Why should a particle, I don't care what massless, what why do particles move at the speed of light? Why is the maximum speed limit in the universe the speed of light? What is this thing with the speed of light? And why is it constant? So this particle always moves at the speed of light relative to an observer. Okay, we'll figure it out why this relative observer, but why does the particle always move at the speed of light? All right, so we have two big questions. Why should a particle move at a constant speed at the speed of light, always at that speed? Okay. And how is it doing this magic trick that it's bouncing back and forth even as it's moving? And we know it has to change the angle in order to hit back at the mirror as it's moving. I mean, we know it must change the angle. That is Einstein's own argument, and that is how we get the time dilation in general in special relativity. So, so Einstein's thought experiment has these gaping holes in them. All right, so let's resolve them. So we know that every particle, right? We know about the particle wave duality from quantum mechanics. We know that there's this issue that sometimes particles behave as waves. So people don't know when. All right, so I came up with my theory, which is based on general relativity. I'm just combining everything into a theory of everything, into a into a unified theory, or I'm also I've basically introduced a unified field, so it might be a unified field theory. So according to me, I'm taking the notion of general relativity's fabric, that thing that Einstein said that curves. So Einstein said, or people say, that space curves. I disagree with that. I don't think that is the correct theory or the correct explanation of how gravity works and how the universe works. So according to me, we're surrounded by we're embedded in a three-dimensional fabric, which is sort of a solid, sort of a liquid, like it's a liquid very similar to water. It's incompressible, it's unstretchable. So that's the assumption. So we're submerged, the whole experiment is submerged in a liquid called the fabric, or maybe we should start calling it the unified field, because we're going to fit everything in all of science, in all of physics. We're going to fit everything into this one unified field. So we're going to insert, I think everything is already in this one unified field, but we're going to say that gravity is also gravitational waves and gravity. Everything lives in this one unified field, and quantum mechanics and the dual slit, the two slit experiment, everything should be explained in one unified field. And that's where what I see, that's where the data is pushing me. I'm being pushed to the wall with my back against the wall by the data, by the experiments. I'm being pushed against the wall and I'm being forced to unify all of physics into one unified field theory. So the unified field is, it basically starts from I don't want to say from general relativity, because I start from Galileo's equivalence principle that Galileo discovered, that all objects, no matter what their mass is, they all seem to fall at the same rate. So, meaning its mass, the test mass is invariant to the behavior of gravity. Meaning, even if it's a massless particle, it should accelerate towards Earth at the same rate as a 1 kilo. So that already forced me into a theory of gravity that is very similar to general relativity. Oops, Siri keeps responding every time I say theory. All right, so from there, I was forced into anyway. Okay, well, we'll come back to that. Why I was forced. You can see all the videos how it evolved in my mind. It happened kind of slowly and then fast, whatever. Okay, so there's this unified field, or what Einstein called space itself, or the fabric of space. And I don't say space time. And today we're gonna understand why I never say space time. And people that say space time, even I think Einstein said it, I think it's wrong. All right, so how does this work, right? So we had two questions. Let me show you how I answer these two questions. And special relativity, of course, still works. I'm going to give you a framework in which special relativity will still work, and general and quantum mechanics. Everything is going to live in this one new framework. So it's really wonderful. All right. So it seems to be the more correct theory. If we go by the definition of science, what is the correct theory? Well, it's the simplest one. So people say that they cannot fit general relativity and quantum mechanics. Well, I'm forced to put them together. I'm forced to put them together. I have no choice. Let's show it. So we're gonna have this fabric. It's a three-dimensional fabric. I'm only going to show this in 2D because I don't know how to draw so well. Uh, so we're going to embed this experiment in a fabric, in a liquid. All right. Okay, that's the first step. Second step is, so particles cannot move. That's my principles or my axioms. So particles, my first axiom is we're embedded in a fabric. It's a liquid for now. The second, um, axiom that I'm going to present, right? We're allowed to present, we have to present every system according to the incompleteness theorem. Every system must be based on axioms that we have to assume are true in order to build our system on them. So here are my axioms. So axiom 2 is that particles cannot move through this fabric. If particles could move through the fabric, then they could move, of course, faster than the speed of light. They wouldn't have any reason to be limited by any speed. Why would a particle moving through a fabric, if the particle can move through a fabric, why should it be limited by any speed? So therefore, I have to assume, meaning this is my axiom, that particles cannot move relative to an inert. Everything is, of course, just like in special and general relativity. So everything I'm saying is relative to an inertial observer. So particles cannot move relative to an inertial observer because an inertial observer sees this fabric that everything moves through the fabric. Okay, so what does move? So every particle, in order to move through the fabric, must convert into a wave. And this is an old principle introduced by de Broglie. So de Broglie had this idea after Einstein said that photons are both particles and waves. De Broglie came in and he said, let's do that with electrons. And he predicted that the double slit experiment will be reproduced with an electron. And since then, I think the double slit experiment has been reproduced by even very big particles. But these particles, notice, as big as they are, they're not visible. And I can explain why when an object is visible, you cannot reproduce. It destroys the double slit experiment, and you stop getting the Schrodinger wave equation. You stop seeing a wave distribution, and you go back to a particle distribution. We'll come back to that. All right, so principle 2, particles cannot move through the fabric. They must convert into a wave. All right, so this particle, this photon, in order to move, is now a wave. And as a wave, like everything here is three-dimensional. So as a wave, it's a three-dimensional wave. So imagine a three-dimensional wave. Three-dimensional wave is very similar if you see an explosion. That's a three-dimensional, you could say it's a three-dimensional explosion, which is a motion of particles. But imagine a three-dimensional explosion that causes a shock wave, a three-dimensional shock wave to travel through the atmosphere. Sometimes you see them, especially if you see simulations of jets fighting in DCS simulator. So when a jet blows up, you can see, or when a sidewinder or there is an explosion in midair, you see a three-dimensional wave propagating. So every wave we need to imagine is a three-dimensional wave, and this is derived directly from Maxwell's equations. And I understand that this is also derivable from Einstein's general relativity field equation. So I never say, by the way, in all my entire unification, I never bring up any new science and I never conflict with any existing science. So I'm not a conspiracy theorist. I'm not saying anyone has lied to you. I'm just going to say that certain things are wrong, the wrong explanations. I'll give you the alternative, my explanation. I'll explain to you why I think it's better. But I'm not going to conflict with any data that we have. I'm not able to explain everything just yet. I haven't thought out everything, but my intuition is that all quantum mechanical experiments can be explained by my explanation, my unified field theory. And of course, general and special relativity are obviously explained by it too. So I'm starting from everything that we know, and I'm putting it all together. It's like I'm just fitting in. I just noticed a bunch of puzzle pieces that There's experts in each puzzle piece. There's people who are experts in all the puzzle pieces, but for some reason, no one has figured out how to put the puzzle together. I am by no means an expert in this puzzle game and the puzzle pieces. I'm not an expert. I'm not a complete novice. I know just a little bit, maybe over the average person, but I think I'm able to put it together. I think I'm able to put the puzzle together, even though I don't understand the pieces completely, but good enough. I think I would compare myself to the way that the right in the beginning people used to think that the earth is at the center, maybe before Galileo and stuff, and they used to have very intricate mathematics and very intricate rules in order to explain the retrograde of the planets, that Mars went back and forth and all the planets kept going, or whatever, they kept going back and forth in the sky and no one had an explanation. So they came up, the ancient ones, they came up with intricate explanations to explain the retrograde, the backwards motion of the planets. And then came Galileo and he said, "Wait, we can make it much simpler. We don't need all this intricate math. All we need to know is that the earth is at the center." I think other people have come up with this explanation. It's a much simpler explanation. You don't need to know any advanced mathematics and any advanced ideas of retrograde and stuff. You don't need to know that. All you need to know is that the sun is at the center, and then everything makes sense. So that if you imagine, if you run a thought experiment that you're on the earth, yeah, you would see the retrograde. But that's because basically an illusion. It's because everything is going circles or ellipses around the sun. So that's the way I see it. So everyone today has very intricate explanations to the different parts of physics. I think I can put it together so that you don't need to understand the complexities. Um, I think it might be like that. And without understanding the complexities, you can understand a much simpler model. And that simpler model gives you maybe even more predictive powers than understanding all the intricate mathematics of the different puzzle pieces. I don't know. That's my intuition of what's going on with my theory. All right, let's continue. So a particle, in order to move, is a three-dimensional wave that propagates in every direction, but it will interact with the other mirror, and of course it will interact with the mirror wherever it is. So it's not going to interact with the mirror if by the time it hits here, the mirror is no longer here, the mirror is somewhere else. So it's going to interact correctly without being a genius and without knowing and without all the problems. It's going to easily interact with the mirror over here, and then it's going to again bounce as a wave. It's going to bounce everywhere. This is a three-dimensional wave. It's always a three-dimensional wave. It's coming out at us as well, and it's going to end up getting interacting over here and getting discovered by a detector. Or even without a detector, it's going to be able to bounce back and forth. And this makes the first question, where we've just answered the first question using quantum mechanics, using wave particle duality and de Broglie and Maxwell. So we're using known science in order to answer a relatively simple question that maybe others have answered. That's fine. But the question would be, why would the particle become a wave? According to current quantum mechanics, it sometimes is a particle. No, sorry, they say it's a wave until we detect it, until we observe it. And when we observe it, it becomes a particle. So according to me, that's not true. It's when it moves, it must be a wave. And when it's detected, meaning it's now stationary, it's been absorbed into another system, it does that as a particle, according to de Broglie. But as it moves, it's always a wave. So it's nothing to do with detection. It's not that the detection, it's not the observation, it's not Schrodinger's cat. Schrodinger's cat is incorrect. Schrodinger's thought experiment is incorrect because it is not. The cat is not both dead and alive until we observe it. There is no act of observation. It's the act of interacting. When the wave interacts and therefore stops, in order to interact, it has to stop, basically, and decide to become a particle, according to the boil, right? Decide, quote unquote. I don't know this decision mechanism. We'll come back to it. This is work in progress. So, all right, lost my train of thought. Let's continue. So, okay, that's the first question. So we answered the first question. Okay, so the next, but before we complete the answer, so this is part of my theory. So according to me, in order to understand Maxwell, you have to assume, right? Basically, Maxwell assumed that there is an ether or there is this fabric because I don't know if he assumed it, but okay. So according to Maxwell, from Maxwell we can see that light is a wave. Okay, so according to Maxwell, we know that light is a wave. It's an electromagnetic wave, and Maxwell unified electricity and magnetism. Okay, but it as a wave, the way we understand waves can only wave inside something. You cannot understand a wave unless it's waving inside something. That's the definition of a wave. You cannot have a wave by definition in a vacuum. And in general relativity, we have a quote from Newton. So again, I'm not going against any consensus science. I'm just going to quote Newton. So, you know, it's not my idea. So when I heard Newton say the following quote, that boosted me to decide that there cannot be a vacuum. So Newton said in a letter to somebody, I don't remember, he said, if you think that gravity, the force of gravity is mediated by the vacuum or over the vacuum, you have to be out of your mind. You have to be insane. So I think Newton would say that we're all insane. That people today in modern science, that we believe that gravity is acting over a vacuum, he would say that's insane. So there's many reasons to believe that there is a fabric because gravity cannot be mediated over a vacuum according to Newton, and because gravitational waves, even Einstein said he predicted they would move at the speed of light. So that indicates again that there is a fabric through which a wave is moving. And then we have this issue of the speed of light. Again, this is reminiscent of the property of the medium through which a wave is traveling. So right now I'm speaking and the waves are traveling at the speed of sound, not because of my voice, but because of the properties of air. And if the sound travels through my desk, it's going to move faster because of the desk. That's how waves move through solids and through water and so on. So the speed of light should be determined by the properties of the medium. Right, the notion of the speed of light that should remind us, that should tell us, oh, there is a fabric, there is a medium through which light is traveling as a wave. Gravitational waves are traveling as a wave through something. So relative to an inertial observer, this solid is stationary, so I can't feel it. I'm embedded in it as I'm stationary. When I move my hand relative to my eyes must become a wave. So but we know this from quantum field theory. In quantum field theory, we say that everything is a wave. Everything is described by a wave. So again, I'm not saying anything new. So of course, my hand, as I'm waving it, it's waving through a solid. So it must become a wave. Okay. And that's why I can't move my hand faster than light, because I cannot, because the maximum speed of a wave in the medium is the speed of that is determined by the medium. And by the way, the fact that I can move my hand slower, or it seems to be that I'm moving my hand slower than the speed of light, well, that's the Higgs mechanism. So again, the Higgs mechanism just sits inside this fabric, and it is the Higgs mechanism is the mechanism by which this fabric, this unified field, it endows mass onto particles because of how these particles interact with the unified field. That's the Higgs mechanism. The Higgs mechanism is just a mechanism, it's just a trait of this unified field space fabric. Okay. Obviously I can talk forever about this. So let's decide to at least the first point stop here. So we have a wave waving back and forth, and that's why it doesn't care that the mirrors are moving. It's always going to succeed in bouncing back and forth. Okay, now, so why is the speed of the particle always the speed of light? Why does light move always at the speed of light, right? That was the second question. The first question is, how does it manage to know to move at an angle? Well, we resolve that. It's because the particle is not a particle, it's really a wave. When it moves, it's a wave. And the second question should be self evident. Once we say it's a wave, then waves always move at a constant speed relative to, well, it's not relative to an observer. It just depends on the media, on the medium. And we already said that the medium is stationary if the inertial observer is inertial, is stationary. So an inertial observer is not necessarily stationary, but an inertial observer cannot determine that he is or is not stationary because there is no absolute location and there is no absolute motion in the universe. So if I always go back to I'm being all alone, I don't know why Einstein didn't start from this thought experiment. So the first thought experiment is I am all alone in a universe, empty universe, with just a spacesuit and some oxygen. All right? So I'm all alone. Now the question is, can I determine my location? Or does it have any meaning to have a location? So the obvious answer is there is no meaning to have a location in a completely empty universe. I don't know what it would mean to have a location. And the second question is, can I have a velocity, a speed? So again, I don't know what those two terms are just those two terms are just undefined as far as I'm concerned. Location and velocity are undefined for an inertial observer. So an inertial observer is allowed to say, as far as I can tell, I'm not moving. So we'll assume that. I think that's basically Einstein's assumption. So we'll go with that. So an inertial observer can claim to be stationary, and therefore the fabric is stationary, and therefore everything moving must be moving as a wave, and as a wave, the velocity or the speed of the wave is determined by the medium, and the medium has been predetermined for all waves to move at the speed of light through this medium. So any phenomenon, any information, or any wave that waves through this, and there is an exception. We'll talk about when a particle is discovered, and this three-dimensional wave, it's a bubble, it pops. We'll come back to it, and that does not need to abide by the speed of light. The speed of light or the speed of the wave is just for waving. So in order to wave through, that's one speed, but in order to interact, that's a different speed. It could be instantaneous. It seems to be from the data. It seems to be instantaneous. So we'll have to assume it's instantaneous. But there is no, I don't think there is information being there is no information being related, I think. That's what the data says. So we'll have to abide by that. But we'll come back to that. That's work in progress. Let's continue. All right, so now we understand it. Okay, so as you can see in my discussion, of this phenomenon of Einstein's thought experiment clock that he reuses. I think he introduced it in his special relativity paper. I don't remember if I read it or not, or I think I just saw it or skimmed to it. So anyway, as far as I know, he introduced this thought experiment of the ticking clock. So now we explained it, I would say, properly. I think Einstein. So we know Einstein did not figure out unified field theory. I think he worked on it for his last 35 years or something at home alone. And as far as we know, he didn't get anywhere. But I think he started from the wrong place. I think he didn't take his his general relativity, his theory of gravity. I don't think I don't think he took it seriously enough. I think he went with the analogy. So people say, yeah, the fabric curving and moving. People say, no, that's just an analogy. The fabric is just an analogy. So if you think the fabric is just an analogy, so you telling me that the moon is being dragged towards Earth by an analogy? So an analogy has such power? The Earth is being pulled into the sun by an analogy? This galaxy is held together by an analogy? Our galactic cluster local neighborhood, is being held together by an analogy? The universe is being held together or blowing up by an analogy? Really? So what kind of a theory is that? The theory that an analogy can pull down the apple from the tree. Right? Einstein came to answer how does the apple move towards the ground, accelerate towards the ground? So the answer is, oh, it's an analogy. Obviously that's a joke. You can't say an analogy. You have to come up with a mechanical explanation. Once you give up, here's where everyone, I think, went wrong. That's my theory of how everyone went wrong. One second, let me just answer my new owner. One second. One second. One second. One second, please. One second, please. One second. One second. Okay, we'll continue. Okay, we'll continue. I'm waiting for a response. Okay, so you can't say it's not a good scientific theory to say an analogy is pulling the apple towards the earth. It has to be something more mechanical. Something has to be pulling the apple towards the earth. So my fabric obviously does it. In my theory, this fabric, the unified field, it's always being dragged towards the earth. So particles with mass are always dragging the unified field inwards. So that's already my quantum what do you call it? Quantum gravity theory. So my quantum gravity theory, I'm basically obviously I'm taking general relativity more seriously. My fabric is not an analogy, it's a real fabric. I understand that people are confused that we're not drowning in this liquid, but this liquid, it's when particles move through it, they become waves and they just move through it. So it shouldn't confuse you. It's just that everything that's moving is waving through, but that's fine because of quantum field theory. Quantum field theory already says that. So I'm not saying anything new. Like, don't blame me. I'm just a messenger. I'm just letting you know everyone is correct. You can just fit everything together and it just fits together. You don't need to fight it. Just don't fight it. Look, if you fight the fabric, I think that's what happened to Einstein. So he didn't take the fabric seriously enough. He didn't really believe in it. So that's where everything breaks down. Then you when you avoid where the truth is pushing you, the truth, the data is pushing you back and back and back. And then you finally, your back is against the wall. And and that's it. You're forced to admit, okay, there is a fabric and it's a liquid, a solid, it's really, really strong. It's really hard, and that is what everything is waving through. And the particle wave duality is explained. Everything works. Everything fits. As they say in Star Trek, if the shoe fits, wear it. All right. So okay, so everything fits, right? This experiment now works. Now this video is titled "Stop Saying Space Time." So as you can see, there is no space time. There's no reason to say that weird name, space time. What space time? There is no space time. There's just space. Space is a fabric, just like Einstein said in general relativity. Everything moves as a wave, just like De Broglie said, and just like we said in quantum field theory, everything moves as a wave through this field. And because everything moves as a wave, there is a constant speed c. And because of that, clocks in different frames of different reference seem to tick at different rates. That's it. It's all explained. There's no issue. There's no space time. Time is measured by a clock ticking. It's just an effect. Time is a side effect of the motion of space, the relative motion of space, or, yeah, the relative motion of things through space. Or the relative, we'll get to, I'll make maybe another video about the relative motion of space. But you can already see in this basic thought experiment, there is no space time, there's just space. And space induces the effect of the slowing down or the dilation of time. So, time dilation is just a side effect of this unified field theory of special relativity. There's no space time. There's space, things wave through space at a constant speed, just like Einstein assumed. Light is always constant relative to every inertial observer. That's explained by the fabric from general relativity, from Einstein's field equations. Everything fits. So, so there is no space time. There's only space, and time is just an experiment. Time is just a thought experiment, and time is what we witness. Fine. It's also we can measure time. Okay, but in this thought experiment, you can already see there is no space time. You can say there is time, as is, right? Time, like every other scientific theory, we come up with a theory of time. And what is time? Well, we can define time in scientific terms because we can measure time. If it's measurable, reproducible, and all those things, right? That's all we need. We have a mechanical theory of time. The mechanical theory of time is actually very simple. It's it's expressed in a mechanical contraption. Here is the mechanical contraption that explains time. This is a theory of time. I don't think anyone has ever come up with a theory of time. This is a theory of time. Actually, you could say Einstein came up with a theory of time, but it was improperly, that everything was improper, not everything. The two parts that I discussed were improper about it, at least the way I've been taught by everybody uh, in the world and everybody on YouTube. So, a theory of time, as I presented it here, all we need to say is this is this is how we measure time, right? So there is no absolute time. Time doesn't exist absolutely. There's only a measurable scientific experiment that we can reproduce this notion of time. So so time is just what we measure. That time is something that an inertial observer experiences. It's a in a ticking clock. For example, of course, we don't need to do it with a photon. We can do it. I mean, the photon, I guess, is the easiest. This is the most straightforward, which is also an electromagnetic wave. So we could do it. Okay, so it's so, but this is the theory of time. I would say this is the theory of time, and I'm separating time from space. Space is the more, I would say, the more real thing, meaning I haven't explained space yet, so I don't know what space is yet. I'm it's work in progress. I'm working on it. It seems like space is still a bunch of particles interconnected with some sort of springs between them. I don't know their size. They seem to have a these particles seem to have a mass. I don't know what these particles are. I don't know basically anything about them specific. I know in general the way this fabric is composed of these particles is that it gives us the speed of light c. It also gives us gravity because this fabric can collapse into a gravitational well. It also gives us the Higgs mechanism, so it imparts mass onto particles, massless particles that interact with these particles, with the fabric. Anyway, that's a different topic. But I think I'm separating space from time. Please stop saying, if you say space time, then I know you disagree with me. So you need to explain to me why you disagree with me, because I think I'm giving a better theory than Einstein. With all due respect, of course, I love Einstein. I respect Einstein. I respect everyone just the same. There's nothing to do with disrespect, but I think if Einstein would have heard my presentation, he would have said, "Wonderful." He would have really enjoyed this presentation. So this presentation is, let's make this presentation in honor of the great Einstein that we all love absolutely. Okay, everyone, let's stop here, and we'll discuss other notions of my new improved unified field theory on the next video. Have a great rest of your day. Bye bye.